Today what we're going to do is continue our discussion of factor markets by essentially talking about how capital markets impact real-world decisions. So last time we talked about the capital market. We talked about essentially the way that firms finance their capital is by going to a pool of savings that individuals decide on how much to make. Individuals make an intertemporal choice on how much to save. Actually, technically, make an intertemporal choice about how much to consume each period. That then yields an amount of savings. And then based on that pool of savings, firms borrow at some interest rate, I, and they decide how much to invest. Now, today we're going to talk about a number of interesting applications that arise from capital markets that are important in the real world. I'm going to start by talking about the concept of present value. Present value. Now, the key insight when we think about capital markets is that $1 tomorrow is worth less than $1 today. $1 tomorrow is worth less than $1 today. That's because if you had the dollar today, you could productively invest it and have more than $1 tomorrow. So $1 today is worth more because you could do something productive with that dollar if you had it today. Okay? What that means is that dollars in different periods are worth different things. You can't just add them up. Okay? The analogy I like is thinking about, imagine you had a pound of apples, a pound of steak, and a pound of gold. You wouldn't just add them up and say, I have 3 pounds. That'd be useless. You'd want to know what each is worth, and you want to add up the dollar value of them. Okay? It's a similar thing with money received over time. You can't just say, I'm getting $1 today, $1 next year, and $1 5 years from now. They aren't the same thing. Money received at different points of time are worth different amounts because money received in the future forgoes the possibility of investing it today. Okay? So what do we do to deal with this? Well, in economics, we deal with this by the concept of present value. Present value is the value of every period's payments in terms of today. So the way we deal with the fact that money in different periods is worth different amounts is by what we call discounting it back to today. We essentially take future dollars and discount them back to today to get present value. We discount them because future dollars are worth less. Okay? So let's think of it this way. Suppose that the interest rate is 10%. Let's do an example. Imagine the interest rate I is 10%. And let's say that you want to have $100 next year. You want next year you want to have $100. Well, how much do you have to put in the bank today? Okay? Well, we can solve the equation, which is that you want the amount you put in the bank today, let's call that Y, times 1 plus the interest rate, because that's what you make by having the bank, equal to 100. That's the equation you want to solve, right? The amount you put in today, Y, times 1 plus the interest rate, you want that to be equal to 100. So what that says is that Y equals 90.9. If you put $90.90 in the bank today at a 10% interest rate, you will have $100 tomorrow. More generally, we say that the present value of any future payment is the future value, the amount you get in the future, over 1 plus I to the power little t, where t is the periods in the future. So money received t periods in the future today is worth the amount you get in the future over 1 plus I to the t. Okay? So that is our general formula for how we think about present value. You take all the future payments and you discount them back to today by dividing by 1 plus I to the t. Now that works well if there's a future payment and one future payment coming. But what if, as in many cases, there's a whole stream of future payments coming? Well, the logic then is the same. You just want to take each future payment and discount it by how far it is in the future. Okay? So suppose that you say that you want me to loan you $30 and that you'll pay me back $10 each of the next 3 years. Okay? And suppose the interest rate's 10%. Well, I will say no to that. Because I will say, if you're going to pay me back $10 each of the next 3 years, then what's the present value of that? The present value is next year's $10 over 1.1, because the interest rate's 10%, plus the $10 the year after that, over 1.1 squared plus the $10 the year after that over 1.1 cubed, which if I add it up is $24.87. So I am losing money. If I give you $30 today and have you give me $10 back each of the next 3 years, I'm losing money. Why? Because if I'd simply taken that money and invested in the bank, I would have had a lot more than the $30 I'm going to get for you after 3 years. Okay? So the money that comes in the future must be discounted back to today. That's the key insight of present value. You can't just add it up. You've got to put it in today's terms by discounting it by the interest rate. And how far into the future? Yeah.
So aside from just the change in value that's caused by interest, how do we take into consideration the fact that like the value of the currency itself also changes over time?
We're assuming now inflation's zero. So we're assuming right now, we're not dealing with inflation. We're assuming a world where prices don't change. We'll come back to inflation in a few minutes. But for now, just assume that prices don't change. Okay? So basically, essentially, the formula then for the present value, your general formula for present value you need to know is that present value equals, if you get a flat stream of payment F for a number of periods, it's F times 1 over 1 plus I to the T plus 1 over 1 plus I to the 1 plus 1 over 1 plus I squared plus 1 over 1 plus I cubed plus dot, 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 for how many periods you get it. So if you're getting a payment F over a certain number of periods, you've got to discount it by how many periods you're going to get it. Okay? Or more generally, a common formula we'll ask you to use in this class is to think about the formula for a perpetuity. A perpetuity is a flat payment you get forever. So if we take the infinite sum of this equation, we can summarize it as present value approximately equals F over the interest rate. So if I promise you to pay you forever a certain amount F, that is worth F over the interest rate. So in other words, if the interest rate's 10%, a promise to pay you $10 forever is worth about $100. That's just the infinite sum. If you read A Beautiful Mind, John Nash drew that in his head. But I can't, but that's just the formula. Okay? So basically, that is the general formula for a perpetuity. And that makes life easy. We'll give you a lot of examples where because if I say I want you to pay me for 8 years in the future, you got to write out 8 terms here. It's a pain in the ass. So what we'll say is money forever, and then you can just use this shortcut, which is the present value for a perpetuity. It's just F over I. Okay? Questions about that? Yeah?
Does this also assume the interest rate doesn't change over time?
That's a great point. Yes, I'm assuming a constant interest rate over time. Now, in reality, you'd want to have each period's interest rate here, and then you can't use this formula because the interest rate itself is changing. Very good point. Okay? Now, the other way to think about this is instead of thinking just this will be easy for most of you, but just it's useful to think it through. Let's flip on its head and not think about present value. Let's think about future value. This is a useful tool as well. Let's flip it on its head. Okay? So let's think about the value of a future stream of payments. Well, by the same logic we wrote before, future value, by the same logic we wrote before, if you're going to have money that's T years in the future value of that money that you're going to get, okay, if you're going to basically take your money and invest it, if you're going to have money that you're going to invest today and put it in the bank at some interest rate, then the future value is the amount you put in times 1 plus the interest rate to the T. So I've simply reversed that formula, present value, future value. So basically, future value, if you put money in the bank at some interest rate, you're going to get to have, over time, that money times 1 plus I to the T. Now, the reason we write this formula out and sort of flip it for you is because I want to highlight the key feature here that I want to drill into your heads. One of the, 10 things I most care you leave this course thinking about, if you're not going to major in economics, or remembering, is the beauty of compounding. Which is that with a formula like this, you earn interest on your interest. If you leave money in the bank, you don't just earn interest on the initial amount you put in. you earn interest on the interest you earn over time. Okay? And this can be quite large. So let's do a simple example. Okay? Just to show you how big this can be and to get you all thinking about what you should do with your money when you get a job. Okay, imagine you plan to work full-time from age 22 to age 70. A little daunting to think about now. Probably most people retire after 70 by the time you guys retire. But let's just think about 22 to 70. Okay? And let's say that you can save at a constant 7% interest rate. Inflation's 0, the interest rate's constant. Make life easy. 7% interest rate. Okay? And let's consider two different plans you have for savings. Plan one. Plan one is that you're going to save $3,000 a year for the first 15 years that you work and then stop saving. $3,000 for 15 years, then you're just going to leave that in the bank, leave it alone, never save anymore. Just let that money sit in the bank. Okay? Well, in that case, what will you have? Well, after the first 15 years of putting $3,000 in the bank every year, if you work out the math, you will have $75,000, $75,387 after 15 years. Okay, that's not just 15 years times, that's bigger than 15 times 3,000 because you're earning interest along the way. Okay, that's 15 years. Then you're just going to let that sit there. And that's going to sit there. Remember, after 15 years, you started working at 22, you're only 37 years old. That's going to then sit there for the next 33 years. You're not going to touch it, you're not going to save any more. What that means is after 33 years, this turns into 75,387 times 1.07 to the 33rd. Okay, after 33 years, or $703,000. 703,010. Okay? So you save $3,000. That's not a lot of money. You guys are going to make a lot of money. $3,000 for 15 years, and then you never had to save again. Contrast that with a different approach. Let's say you say, look, that's stupid. I'm young. I'm going to party. I'll worry about retirement when retirement's close. I'm going to save nothing the first 15 years. And then I'm going to save $3,000 every year. First 15 years, I'm going to save nothing. Then I'll save $3,000 every year. Okay? Well, if you do that and do the math, you end up with, when you retire, $356,800. Think about this for 1 second. In this case, you save for more than twice as many years. You saved for 33 years, and you ended up with half as much. That's the miracle of compounding. The earlier you save, the more money you can make it along the way. And that's why you guys need to start saving right away. Yeah?
What was plan 2 again?
Plan 2 was I do nothing the first 15 years. Then I save for the remaining 30, I save $3,000 a year for the remaining 30 years of my career. Okay? So literally in plan 1, I save for 15 years and then I stop. Here I save for 33 years. But by starting earlier and using the miracle of compounding, I end up with twice as much money. Okay? Now, this is actually pretty, this is one of the few things in this class my kids could understand when they were little. Because having you been to the Boston Science Museum? Any of you guys been? Okay. There's a little kid area where they've got this ramp. And you can essentially drop balls down a ramp. And one ramp is flat and then steep. And one ramp is steep and then flat. And of course, the one that's steep and then flat wins. It's faster. And that's just because of compounding. That's because acceleration's compounding. Okay? So basically, the point is that the earlier you start saving, the more money you'll have. And that's why you guys should pay attention when you're offered a job and offered a 401k and not think retirement, I'll never retire. You say, no, I want to save now, because the more I save now, the more that'll compound by the time I retire. Okay? Now, you can actually see this. It's not just MIT students have to think about this, but professional athletes. So probably none of you have heard of Bobby Bonilla. Any of you guys heard of Bobby Bonilla? No? Okay, well, if you were 25 years ago in this class, if you were into sports, you would have heard Bobby Bonilla. He was a pretty good player in his time. And he retired, but by the end of his career, he was kind of a slacker. He wasn't really worth much. He was playing for the Mets. And the Mets said, look, in 1999, they said, look, we basically want to pay you off to leave the team. You have a contract. We're just going to basically pay the remaining $5.9 million on your contract in 1999, give you the money. Most athletes would have said, great, I'm off to Vegas. Bobby Bonilla didn't. He said, well, look, I've got enough money right now, but I might need the money later. So instead, why don't you defer the money at an 8% interest rate, and pay me starting in 2011 when I'm getting close to retirement and need the money. They were like, great. That's like, great. We don't have to pay you now. That's great. Well, Bobby Bonilla, by the time his payment started in 2011, they'd grown to $30 million. And every year on a certain day, it just passed recently, they call it Bobby Bonilla Day. Bobby Bonilla, who's now like 70 years old, gets a $1 million check from the Mets every year. Okay? Because he was patient enough to put this off and get the virtue of compounding. Okay? So this is sort of, if Bobby Bonilla, a stupid baseball player can do it, you guys can do it. So make sure that you guys are saving when you start your jobs. Okay, questions about that? Okay, now let's get a little bit realistic, and let's recognize that in life prices aren't constant, but rather we have inflation. And how does that affect our thinking here? How does inflation affect the way we think about this problem? Well, it turns out it actually adds one step, but it's actually a pretty easy step to put in. It actually turns out you can add inflation without doing a whole lot of work. So let's talk about first what inflation is. Inflation is the rise in the price level year over year. Technically, the inflation rate is a percentage concept. It's the percent rise in the price level year after year. And you might say the price level of what? Of a banana, of a computer, of what? Well, what the government does is they form something called the Consumer Price Index, the CPI. Did I talk about the CPI yet? Okay, I'm sorry, I hate repeating myself. Okay, so they form something called the Consumer Price Index. What's the Consumer Price Index? Literally, the government every quarter, I believe it is, and maybe every month, goes out and gets the prices of a basket of hundreds of goods. They literally say, what does a banana cost this month compared to last month? What does a laptop cost this month compared to last month, etc. So they go out and they price this bundle of goods, and then literally they just ask, how has the price, they then take a weighted average of that bundle, where the weights are consumer spending. So consumers spend a lot more of their income on housing than bananas. So the price of housing gets a lot more weight in the CPI than does the price of bananas. So actually a weighted average of prices in society, and then they create an index. 1982 is normalized to 1. And they just say how much, in percentage terms, did that weighted average bundle go up in price. Okay? And you can see that in figure 17.1. Here's historical CPI. So basically what you see is this is the level of the CPI, which is sort of meaningless. We care about is inflation, which is the year-to-year percentage change in the CPI. And what you can see is basically it's going up. Prices are going up. It went up very steeply. If you look from 1970 to 1980, the slope there is much higher than the slope before or after. We had very rapid inflation in the 1970s. It then since flattened, and inflation has been much slower. And inflation averages about 3% a year. Okay? So basically, that's how we measure inflation. Now, the question is, how does that affect our thinking about present value if there's actually inflation? And the bottom line is, we don't care about dollars. We care about how many goods we can buy. Therefore, it doesn't matter what's happening to how much money we have. It matters what's happening to how many goods we can buy. Therefore, what we care about is not what we call the nominal interest rate. We care about what we call the real interest rate, R, which we define as the nominal interest rate, which is what we've been talking about, we see advertised in a bank, minus the rate of inflation, which for some reason we use pi, even though that's also profits. So sorry about that. Okay? So we define the real interest rate as the nominal interest rate minus the inflation rate. Okay? The nominal interest rate, the real interest rate, the nominal rate minus the inflation rate. And what the real interest rate measures is how much more I have in terms of goods I can consume, not how much more I have in terms of dollars, which actually in the end doesn't matter. Okay? So suppose that I'm going to save $100 at a 10% interest rate. Let's go simple example. I'll save $100 at a 10% interest rate. Okay? Then next year I'll have $110. But that's irrelevant. What I want to know is how many goods can I buy next year? So for example, let's say you spend all your money on Skittles. That's all you buy. Okay? And let's say Skittles cost $1 this year, and there's no inflation, so those cost $1 next year. Then what that means with a 10% interest rate is you can buy 10 more bags of Skittles next year. This year, your $100 could buy you 100 bags of Skittles. Next year, your $110 can buy 110 bags of Skittles. So you are 10% richer. But now let's say the price of Skittles goes up 10%. Well, what that means is you can only buy the same amount of Skittles next year as you could buy this year. You could buy 100 bags this year and 100 bags next year. So it doesn't matter that you have $110 next year. Who cares? You can only get the same amount of Skittles. What you care about is the goods you can buy. And we wrote down utility. We didn't put dollars in the utility function. We put consumption. So the interest rate you care about is the real interest rate. If the nominal interest rate is 10%, but inflation is 10%, then the real interest rate is 0. You can't buy any more goods next year. All the money you made by putting in the bank got eaten up by how much more expensive things are. So what that means is all the math we've done and everything we'll talk about all goes through. You just need to be thinking about using the real interest rate, not the nominal interest rate. Okay? But otherwise, everything we've done goes through. You just need to essentially think about this in terms of how many goods you can buy, not how much money you have. Now, this isn't quite, let me just take 2 minutes and do a little macroeconomics. This isn't quite as simple as it sounds because, of course, you see in the bank I, in the bank window I. You don't see pi. You don't see inflation. That's all revealed ex post. So really, technically, you don't have to know this. It's just for those who care. You don't have to test. Technically, what you really want is expected inflation, right? When you think of putting in the money in the bank, you know you'll earn 3%. The real interest rate is that minus what you think inflation is going to be, right? So it actually becomes complicated. It's not as simple. Ex post, it's easy to find the real interest rate. Ex ante, it's not so easy because it depends on what you think inflation is going to be. So there's some tricks there. There's also a bunch of tricks in measuring the inflation rate. So for example, like I said, the Bureau of Labor Statistics goes out and has a bundle of 600 goods, and it gets their prices. But what is a good? I mean, a banana is a banana. But a laptop, what the hell is a laptop? How much RAM does it have? What's the graphics card? How fancy is the display? Well, the Bureau of Labor Statistics doesn't go out and price literally hundreds of laptops. It prices 1 or 2. And the problem with that is the following. Let's say you find that today a laptop is 1,000, and tomorrow it's 1,500. But it can do, let's say today a laptop's 1,000, and tomorrow it's 1,500, but it can do a ton more stuff. Well, we would say inflation's 50%, but that's not really right. Because the good you're consuming is not the laptop, it's the computing ability of the laptop. And that's gone up. So to say inflation's 50% is wrong. Inflation's 50% minus the quality improvement of the better laptop you got. Think of it another way. Imagine laptop prices didn't go up, but RAM doubled. Okay? Would you say you're no better off buying a laptop with twice as much RAM at the same price? No, you're better off. But our inflation concept would say, no, you're the same off. So the trick here is it's simple in practice, and we'll pretend it's simple. Just say R is I minus pi. But 2 tricks. A, it's expected pi, which is hard to guess. And B, inflation is really hard to measure because there's things like quality bias and other things. There's a whole field of macroeconomics worrying about inflation measurement. So I won't spend a lot of time on it. But it's just sort of the kind of interesting, we just to sort of talk about how sort of at high level we go through things here. Like everything else in this class, largely we get it right. Largely expected inflation is not too badly modeled by last year's inflation. And quality bias we can model and stuff. So this isn't a bad model, but it just sort of points to some of the subtleties you have to deal with in reality when you try to implement these basic sort of formulations. Okay? Now, with that in mind, I'm going to now say, let's assume inflation's 0 again. Okay? So we'll go back and use I, and we'll use I interchangeably with R for the rest of this course. Okay? Unless asked differently. Unless told differently, assume inflation's 0. So I and R are interchangeable. With that in mind, let's go to the next topic, which is taking these tools, how do we model choices over time? How do people model? How do people make decisions over time? And there's a simple answer. So this is tricky because if I said to you, hey, I'm going to give, would you want $30 or $50? You'd say, I want $50. But actually, you shouldn't say that. You should say, over what period of time am I getting the 30? And over what period of time am I getting the 50? If it's today, I want 50. But if the 50 is 20 years in the future and the 30 is today, I might want the 30. What that means is you have to evaluate choices in present value terms. You can't just add up the money. You have to evaluate those choices in present value terms. And then you need to pick the option with the highest present value. So once again, let's come back to athletes because athletic contracts deal with this all the time. Let's imagine an athlete considering 2 different contracts. Okay? Contract 1 contract A pays $1 million today. Contract B, okay, pays $500,000 today and $1.5 million in 10 years. Okay? Now, when you read in the newspaper, you'll see this guy got offered $1 million, this guy got offered $2 million. That's what the newspaper will say. But that's wrong. Because these are paid at different periods of time that are different amounts. Indeed, the present value of the first contract is what? $1 million. It's today. What's the present value of the second contract? Someone tell me how I'd write that down. How to write down the present value of the second contract. Yeah.
500,000 plus 1.5 million over 1 plus whatever the interest rate is based on time.
Exactly. 1 plus the interest rate to the 10th, right? Because you're getting it in 10 years. Okay? So essentially, that means that whether it's a better deal or not depends on the interest rate. Indeed, if the interest rate is 7%, and the interest rate is 7%, this has a present value of $1.3 million. So it's a good deal. If the interest rate was 14%, then this deal would have a present value of 0.9 million. So it's a worse deal. So whether or not this is a better or worse deal depends on the interest rate. Why is that? Why is this a worse deal the higher the interest rate? Yeah.
Because if he had gotten the money earlier, he could have benefited from being able to collect that interest on it earlier.
Exactly. He could have invested it earlier, gotten the compounding, and had way more money in 10 years. So the higher the interest rate, the more you want to get your money up front and save it. The less valuable is money in the future. Okay? Now, so essentially what this says, you have to always use present value to bring things into current dollars. Now, this is not an abstract concept. Let's take Max Scherzer, who's a pitcher with the Washington Nationals. Max Scherzer, a couple years ago, signed a 7-year, $210 million contract, which he was able to brag was the second highest ever signed by a pitcher, and the 10th highest contract ever signed by any baseball player. 7 years, 210. But in fact, that contract was not, we're going to pay you $30 million for a year for 7 years. It was, we're going to pay you $15 million a year for 14 years. You're going to play for only 7. We're going to pay you over 14 years. So in fact, in present value terms, it was worth somewhat less. If you use the current interest rate when he signed it, which is about 4.7%, it was only worth actually $166 million. Yeah, not too shabby, but suddenly it drops to the 20th most valuable baseball contract and about 4th among pitchers. So Max Scherzer was able to feel better about himself that he signed this valuable contract. But in fact, it was worth less than he thought. I mean, shed no tears for Max Scherzer. He's doing fine. But it was worth less than he thought. Or maybe an example that's more in our mind with the Mega Millions. Think about a lottery winner. So if a Mega Millions winner gets $290 million, okay, which sounds like a great deal, that's paid out over 20 years. So it's not $290 million, it's $14.5 million for each of 20 years. So in present value terms, if we think about a 7% interest rate, then that's not $290 million, it's $164 million. Once again, not too shabby, okay, but a lot less than the advertised amount. So we have to take these dollars and put them in present value, okay? So now here's an interesting question for that. If you look at the recent lottery, okay, you had a choice of one person won $1.6 billion. One person won that. One person in South Carolina won that. And they were given a choice of the $1.6 billion, which was paid actually over 30 years, or a lump sum they could get right away. How should they decide which of those options to take? How should they decide whether to take the $1.6 billion paid over 30 years, so 1.6 over 30, paid in equal installments, over time, versus just getting a lump sum today? Not of 1.6 million, but a lower amount. How should they think about that?
Present value.
They should have present value. They should say, well, what do I think the interest rate's going to be? If I think it's going to be really low, let's say that the interest rate's going to be 0, then which deal should I take? I should spread it out over time, because the money in the future is worth the same as today, so I might as well take the $1.6 billion. But if I think the interest rate's going to be higher, then I should take the money up front and invest that money and earn my own interest. So essentially it becomes a debate of what you think the interest rate is versus what the state thinks the interest rate is. They're setting those two to be equal under some assumption of the interest rate. I don't know what number they chose. Whatever number they chose. It was some number they chose because this is our assumption of the interest rate. You've got to decide, do you think the interest rate's going to be higher or lower? If you think it's going to be higher than the state thinks it is, then you want the money up front and you'll invest it. If you think it's going to be lower, then you should take the money over time, and because the state's giving you basically a better deal. Okay? People understand that? Okay. So now, armed with this, let's go and think about how do firms make investment decisions? How do firms make investment decisions? Remember, investment is about the delay of future consumption, of current consumption for future consumption. It's about putting some aside today by spending money on a machine which will deliver you benefits in the future. Now, this adds one wrinkle to what we've done so far, which is that we've only talked about money that's always positive, some amount you get in the future. When you're making an investment decision, it's a little bit more complicated because you're actually spending money today to make money tomorrow. So in that case, we talk about what we call net present value, which is the same thing. It just allows for negative values. Net present value, which is essentially saying in every period, you want to account for the cost that period and the benefits that period. And you want to invest only if the net present value is greater than 0. So for example, think about a project that has a stream of payments in every period of R sub I. Every period has got a stream of payments of R sub I, and a set of costs of C sub I. The costs are the upfront investment, maybe the maintenance of the machine, whatever it costs to run it. Okay? Then the net present value of that investment is R0 minus C0, comma, R1 minus C1 over 1 plus I, plus, over 1 plus I, plus R2 minus C2 over 1 plus I squared, plus dot, 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 for as many periods as the investment lasts. Okay? That's the net present value of an investment. So basically, what you want to ask is, taking each period's costs and benefits into account, on net, is it greater than 0? Okay? So the key point is that basically, sometimes investments which have upfront costs can be valuable as long as the long-run benefits are large enough. So if you think about an investment that's got 100, so imagine, think about a simple, trivial example of the first period you buy a machine, and it costs $100. So C0 is 100. And let's say for every period thereafter, that machine will deliver you revenues for I greater than 0 of 200. But it will have maintenance costs I greater than 0 of 50. So what's the net present value? Well, the net present value is simply minus 100, and let's say the machine's going to last forever. Minus 100 plus 150 over I. Think about that for a second. Basically what we're saying is you're throwing 100 at it today, so that's negative, but every period in the future you're going to net $150 because you're going to make $250 maintenance costs. And we have the formula, so we just apply the formula for perpetuity. We have a set of future payments of $150. So your net present value is minus 100 plus 150 over I. So let's look at this formula for a second. What does that say? What is the relationship between whether the firm's going to want to invest and the interest rate? What does this imply the relationship is between a firm's desire for investment and the interest rate? As the interest rate goes up, will firms want to do more investment or less investment, and why? Will firms want to be more eager to buy machines or less eager to buy machines, and why as the interest rate goes up? Yeah? Less eager.
Pay more later.
They'll be less eager, say it again, because why?
Because if they're more capital, we need to pay more later.
Yeah. Or the other, I think an easier way to think is borrowing. Just think about they got a bunch of money. Apple's got a bunch of money today they're sitting on. If they buy the machine, they're going to get this return. If they don't buy the machine, they can put it in the bank or invest in Apple stock and get some interest rate I. The higher the higher the interest rate, the less they want to invest. Or think of it this way, the interest rate is the opportunity cost of investment. Okay? The more the firm invests in their machines, the less they can earn saving through some other mechanism. And the price that they pay by forgoing that other savings is I. Okay? Yeah.
So like, does that mean if you're looking at a machine, it's better to like try to to push the cost further into because then like you can't also divide by the 1 plus I.
Basically, you always want to try to make as much money early as you can and make the cost as late as you can. For any given amount, you'd absolutely like to shift your. You'd absolutely like to do that. That's why we'll talk about this in my public finance class. We talk about why when you're paying taxes, you always want to try to find shenanigans that allow you to pay your taxes later. So for any given amount of taxes, the later you pay it, the less it costs you, because you get to earn the interest along the way and then pay it later on. This is a key macroeconomic concept. You'll often hear in the news, high interest rates are bad for business. And you might have thought, why is that? This is why. High interest rates are bad for the economy, you'll hear. Why are high interest rates bad for the economy? You might say, wait a second, that makes no sense. A high interest rate means I earn more in my savings. Why is that bad for the economy? It's bad for the economy because it lowers the demand for capital. Because the higher the interest rate, the less firms actually want to invest, the more they just want to sock their money away in the bank. Okay? So that is kind of, that's the key question. Now, then let me ask another question. If you're a firm, what's the right I to use? If you're a firm thinking about this investment decision, we know the higher I is, the less you want to invest. But what is I? Once again, forget inflation. Inflation's 0. What's the right, what we call firm discount rate? The discount rate is the amount by which firms are going to discount future dollars to bring them back to today. How does the firm think about what I to use? What I should the firm use? Your Apple. Yeah, go ahead.
There's one in I that makes that positive there.
Well, they don't want to invest unless it's positive. That's a good point. But the way they do is they write down the math and they plug in an I. What I do they plug in? Yeah.
Is it published by the government?
Well, it might be. But it's not. There's not one answer. What's the general answer the firm wants to use? What's the general answer? That the firm, if you're a firm thinking about making an investment and you want to discount that investment, what do you want to discount it by? Yeah.
The opportunity cost of the next best return.
The next best thing you could do. So if I'm thinking about building this machine, when I discount it, I want to think about what's the next best thing I could do with that money. That's the discount rate I want to use. So in a world where firms either can buy a machine or put it in the bank, it's easy. It's the bank interest rate. But life's not that easy. Firms have dozens of investments. So where every investment, you want to discount it by the next best thing you can do with the money. It's concept of opportunity cost. That's why it's the very first thing we taught in this class. Opportunity cost is always what drives things. Okay? Questions about that? Now, this isn't just for firms. This same math applies to consumers as well. Let's think about me. A number of years ago, I had to decide whether to insulate my ancient house. Okay? Let's write down the numbers to sort of think how this worked. I had heating bills at that time, back when gas was cheaper, of about $2,000 a year. Was my heating bills for the house. Okay? The best estimate I could get was that if I insulated my house, I would lower my heating costs by 25%. So my heating costs would fall by $500 per year if I insulated my house. And the insulation, but to insulate my house, I had to pay the guy to insulate it, and that cost, the insulation, cost $4,000. How do I think about whether I should insulate or not? How do I think about that decision? What equation should I write down? Yeah.
You minus 4,000 plus 500 over I.
Exactly. I should say, I'll assume I'm going to own the house forever, or at least long enough that I can treat it as forever. and I write down that formula. And what that formula says is that if I think the interest rate's less than 12.5%, I should insulate. If I think the interest rate is more than 12.5%, I should just invest the money and use the returns of that investment to pay my higher heating bills. So it all depends on what the interest rate is. Okay? Now, so that's why, and I did it, I insulated. But that's so the same logic we could think of is basically essentially the same idea as firms. You want to think about the upfront costs and the long-run returns. Okay? Now here's a fun economics question. What if I don't intend to hold the house forever? I would argue I should still use this formula. Why? Yeah?
Because you increase, whenever you decide to sell the house, you increase the value.
Exactly, because I'm increasing the value of an asset that I'll then sell. So presumably by insulating, I've raised the price of my house. How much have I raised it by? Exactly 500 of RI. So I'm going to insulate and sell next year. I should still insulate because I should get 500 of RI more dollars for my house. So in fact, it doesn't matter. If you can sell an asset, then actually your horizon is always infinite. It's not just the short horizon, which is kind of an interesting insight. Okay? So the last thing I want to talk about is the fact that these decisions are not just relevant. You guys are like retirement, business machines, insulation. God, you're old, John. I don't care about any of this stuff. Well, let's talk about something you care about, which is going to college. Let's talk about your decision. You've already made it, but you've got a little sibling, and they're deciding whether to go to college. Okay? Well, and they're not going to go to MIT. They're going to go to a more typical school. And they've got to decide whether to go to college. Well, in fact, their decision is an investment decision, just like any other investment decision. What they're investing in is what we call their human capital. When you get education, you're investing in yourself, just like you invest in a machine. Because you hope, raising the value of what you can do, of what you can earn, by investing in learning stuff. Well, that human capital investment has the same features of any other investment. There's an opportunity cost, which is what? What's the opportunity cost of investing your time in going to college? What's the opportunity cost of going to college? Yeah?
You could get a job.
There's two. One is you could get a job.
You could also invest in tuition.
You could not pay tuition. So if you think about going to college, you're sacrificing two things. All that money you're paying, you could basically invest instead of giving it to some college. And you could be out earning money instead of sitting here listening to me. Okay? So if you think about that, it actually becomes a harder decision you might think. So let's think about a simple example. Let's imagine that if you don't go to college, you work from age 18 to 70. And if you do go to college, you work from age 22 to 70. So we're going to ignore grad school. Okay? 4 years of college, either start working at 18 or start working at 22. And let's say college costs $35,000 a year. Obviously not MIT. Okay, let's say college costs $35,000 a year. Okay? And let's say that if you worked, let's say that if you worked if you worked starting in high school, you could have earned, actually, Patricia, we don't have the, you could have earned $20,000. You could have earned $20,000 if you could have started at $20,000, you've gone to work at age 18. Okay? Well, we can actually graph what this looks like in figure 17.2. 17.2, if you think about age 18, from age 18 to age 22, that's the green area. If you go to college, you give up the $35,000 in tuition and the $20K you could have earned. The bottom line is basically, the red line is your lifetime earnings if you go to high school, if you don't go to college. The green line is your lifetime earnings, the blue line, I'm sorry, is your lifetime earnings if you do go to college. Empirical estimates suggest that at age 22, the typical college graduate earns $45,000. Yes, you're not the typical college graduate. The typical college graduate earns $45,000, and the typical high school non-college educated person earns $28,000. So at age 22, you come out of college earning 45, and if you'd not gone to college, you were earning 28. Not you, but a normal person. Okay? But moreover, not only do you earn more when you leave college, your earnings grows faster. So if you're college educated, it not only means you earn 17K more at 22, it also means your earnings grows faster. So that by age 51, the average college educated person earns $80,000, while the average high school person earns $45,000. So what you see here is the blue line starts above the red line and the gap widens over time. Okay, and maybe I would have learned to clip this on if I hadn't gone to college. Okay, so the gap widens over time. So how do we think about this decision? Well, the cost is the green area. The cost is over 4 years, you could have earned money and you wouldn't have had to pay tuition. The benefit is the yellow area. Over that entire time after graduation, you're making more money. Now, obviously, in terms of size, the yellow area is much, much bigger than the green area. But the yellow area comes later. That's the key thing. So you might look and say, look, it's obvious you go to, if before this lecture, you might say, well, it's obvious you should go to college. Look, the yellow's way bigger than the green. But that's not necessarily true because the green comes now and the yellow comes later. Indeed, if you look at the table, this actually shows the net present value of going to college and high school. And what this shows is at low interest rates, you're much better off going to college. So if there's no interest rate, okay, then college is a much, much better deal. Your net present value of earnings, if you go to, your net present value to go to college is 2.6 million, it's only 1.6 million if you don't go to college. But once the interest rate gets above 8%, it suddenly becomes a worse deal to go to college. That is at only a 9% interest rate, which existed not that long ago, okay, in our history. It was actually a worse deal for an average person to go to college. Yeah?
Isn't that not accounting for financial aid, though? If you didn't have the $35,000 to spend, you wouldn't have been able to invest it.
Well, actually, it's interesting. It depends on the form of financial aid. Why does someone tell me why does it depend on the form of financial aid? Financial aid comes in different forms. So why does it depend on how you get the financial aid? Yeah?
Because if you have to pay it back, then...
If it's a grant, then yeah, you should just take that out of the costs. But if it's a loan, depends what interest rate you get the loan at. If the loan is at the market interest rate, then it's no different, right? But that's a great point, which is why college financial aid comes in two forms. Grants for very low-income people and low-interest loans for other people. Why do we give low-interest loans for college? Because of this graph. Because we're saying we think people need to invest in their education. We're afraid that if they face the regular interest rate, they won't be willing to do it because the green would be bigger than the yellow. So we're actually going to subsidize their interest rate. So that's, you might have thought to yourself, sort of a weird way to get people to go to college is to have a lower student loan interest rate. But in fact, it makes perfect sense. By having a student loan interest rate that's lower than the market rate, you encourage people to go to college because essentially you lower this discount rate for at least on the part that's tuition payments. Okay? So that's actually a very exciting way to think about it, and a very important part of public policy is how we set the interest rate on student loans. For any of you, how many of you guys have a student loan? Do you know? Any of you guys have a student loan? You might not know. Anyway, I set the interest rate on that student loan. So thank you. Actually, when I was in the government, 14 months, the Clinton administration. It was super fun. But looking back, I only got one thing done, which I got to set the interest rate in student loans. So that was kind of fun. But otherwise, it was just a lot of fun being there. So anyway, let's stop there, and we will continue. Let's say Wednesday. So no class on Monday. That's Veterans Day. So we'll meet in a week next Wednesday.